of everything on your homework last night. We did not get a chance to talk about and practice which equation? The politically correct equation. So that's the relationship between KP and KC. That was that was like towards the end, 31, right? Have your homework on your desk. We'll check it shortly. I just want to finish up some of the notes first, and then we'll practice, and then we'll do some actual calculations for something called an ice box or a rice box. I prefer ice box because rice just sounds silly. So it's a modified VDA. So that's our kind of our big deal today. That's what we're going to talk about. All right, so forgive me, I'm going to fly through what we went through yesterday so I can scooch on to the stuff we did not get to. How did we feel about homework, though? It was pretty cool? Yeah? All right, so looking at the particulate diagrams was maybe counting things. They all look the same. You get to count the reactants and the products. Okay. All right, so this is where we did not get to yesterday, so whip out those notes. Let's actually write down a little bit more detail here. So, go back for you, study, stuff like that. But this is what they call the politically correct formula. It's the highlighted formula down here. Why do you think they called it politically correct? They want you to know the order of the equation, right? They want you to know the Kp comes first, Kc comes second. So Kp is equal to Kc times the combination of RT raised to the delta N power. So Kp is politically correct as C. So what you'll notice is that this is going to help us convert from a Kc expression to a Kp expression. Kc has what units in it? Moles per liter or molarity, right? So that's where we use the bracketed concentrations. And then Kp has what units in it? Partial pressures, right? So we'll use no brackets. We'll use the P to represent the partial pressure. So there's a relationship between these two. It's actually ideal gas law. So the relationship between them is this equation, but it's derived from the ideal gas law. So essentially, it's showing the relationship between pressure and concentration. Well, concentration, like you guys just said, was moles per liter, right? So if you take moles, which is N, divide it by V, that gives you moles per liter technically, and that's our concentration relationship between pressure and, Kp and Kc. So that's how we get P, Kp, concentration is Kc. RT, what does our value have to be for dealing with gases? 0.0821 atmosphere liters per mole K. Remember, a lot of times our partial pressures can be, most of the time they'll be in atmospheres, but don't worry too much about it because K doesn't have units anyway, so it doesn't affect it. And then temperature should be in what? Kelvin. And what you have to do is you'll find over the course of the reaction, the change in moles of gas from reactants to products. So the way you calculate delta N, I have it down here for you guys, is just take the moles of gaseous products, subtract the moles of gaseous reactants. So remember, it's always final minus initial so that we get a positive not a positive, we get a overall change, which is we always do final minus initial. So product gases minus reactant gases. And that will be our exponent. At what point in time would Kc equal Kp? At what point, using this equation, would Kp equal Kc? Or when the overall change is 0, so the moles of gas reactants, moles of gaseous products are the same. Okay? Because anything raised to the 0 power is what? Anything raised to 0 power is 1, so Kc multiplied by 1 would be Kp. Okay? All right, so if you pull up your packet, I think it's the second page, the second little, let me look at yours. If you look on the upper right-hand side, it says Kc, Kp. You guys have your packet? Or you can use Miriam's, just don't. Okay. So this is what you're looking at, right? You just want to label this in your notes, Kc, Kp, electronic concept, whatever. Let's do the first one together, and then let's see where you guys can go with this. So consider the equilibrium shown. Sulfur dioxide plus oxygen yields 2 sulfur trioxides. Write the Kp expression. When I say expression, what does that mean? So give me a really general, whatever what. Products or reactants, right? So you're going to have to use this equation and write products or reactants. But when it says Kp, what is it actually looking for in that expression? Partial pressures, right? So here we go. All right, go for it. Please get me started. Sulfur trioxide. Okay, keep going, William.
Over that's sulfur dioxide to the second power.
So partial pressure of sulfur dioxide to the second power. Keep going, Gigi. Times partial pressure of oxygen. Good. Okay, so that's our Kp expression. For the Kp reaction shown in one, the Kp for the reaction shown in one above is 0.25. So we know what it's now equivalent to. Determine the value for the Kp of the reaction shown below. All right, you guys got this one. All right, that question should be done. Anybody want to help me out here? How would you approach this? Raise your hand if you know how to approach this, like in 30 seconds or less. Margaret?
Wouldn't you put like 1 over?
Why would you do 1 over? What do you see the relationship between these two reactions are?
It's the reverse reaction.
Okay, so if you reverse the reaction, what do you do to K?
Put 1 over.
Okay, so you're just going to invert K. Is everybody seeing that right here? Reverse reaction? Okay, so this is reverse, so we're going to invert K. So if K was 0.25, you're going to say Kp prime, usually that's just halogen and something else, is equal to 1 over Kp. Well, that's Kp, so you're technically doing 1 over 0.25, and what is that mathematically? 4. Good. So this Kp prime, which is the reverse reaction, is 4. The first one is 0.25. So what can you guys conclude about this reaction up top? The reactants are favored because the value is small. So if you're looking at the ratio of products to reactants, is there more in the numerator or denominator? More in the denominator, so there's more down here. So the reactants are favored. So in the reverse reaction, you can kind of see the same thing. 4 means greater than 1. Products are favored, but who are the products in this case? The reactants of the previous one, so you can see how that fits both ways. So technically the reactants are more stable, which is why they're more favorable. All right, so keep going. 3. At a particular temperature of 1.25 liter flask contains 0.45 moles of hydrochloric acid, 0.29 moles of hydrogen, 0.45 moles of chlorine. At equilibrium, all species are gaseous. Determine the Kc. So you have to read how it's stating the reactions occurring. But try to write your reaction first. Then write your expression. Then solve for Kc. See what you can do. process, guys? Yeah? Okay, keep calculating. Yeah. All right, so just to be clear, we wrote our balanced chemical equation first. Give me a check, give me a thumbs up. You wrote your balanced chemical equation correct. Formation of HCl, right? So balance it out, diatomic chlorine, diatomic hydrogen, you need 2 HCl's. So expression, make sure you're putting your squared on your HCl. And they gave you all the data points you need, but in moles and liters, so you have to find your own concentrations to plug in. You don't actually have to calculate them yourself, but if you plug them in like this and you put enough parentheses in your calculator, you should get what here? 1.55, good. Okay, so the K is greater than 1. What does that mean about this reaction? Products are favored, good. If I had a graph, and it was concentration versus time, what would the graph look like at the end? Right, so they would be steady sloped, right, zero slope, but the products would be higher. So, I don't know how I started off here. Okay, so it'd be like this, eventually here, but your products would be here. It looks like you still had more products overall. Okay, so we'd have to have 3 lines because we have multiple reactants in a product. But regardless, this is our KC. Can everybody right now tell me the KP value? Why is it the same? Right, so just to show the process of that, we know the equation. Niall, what's the equation for the KP-KC relationship?
KP equals KC times R2 to the power.
So we're just going to verify we all know that both the R and the T are raised to the power of delta N. Okay, so don't mix that. It's not both, or it's not one variable, it's both. So we know the KC is 0.55 or 1.55. We know the R is 0.0821 atmospheres liters per mole K. We know the temperature. What was the temperature here? Oh, that's right. That's why I didn't give it to you, because it's 0. At a particular temperature of 200 Kelvin, okay, so if I gave you a data point, you would be plugging that in here. So if it was 200 Kelvin, you would raise all of this to the delta N. But looking at the reaction, you had 2 moles of gaseous chlorine, 2 moles of gaseous hydrogen chloride, and then 2 moles of gaseous reactant, so 2 minus 2 is 0. But if you did not have a 0, you would be plugging a number in up here. Okay? That should hopefully help with one of those textbook questions. All right? Do me a favor. We're going to go over like 2 more slides, but we're going to grab our laptops first because they take forever to pull up. So let's have the class go grab their laptop. We're going to do a quick activity between notes, okay? Can I go past this? Most of us are saying yes? Okay. We will check this momentarily. I just put the key under Unit 7 documents so that you can kind of target your questions. So you could look at my long-winded explanations, but we'll get back to that shortly. I'm going to have 3 separate groups of people help out here, okay? So the next half of the class, go grab your laptops. So like the rest of you. All right, JT's row and Fatima's row, okay? We're going to look at one experiment and then I'm going to kind of toggle team the rest. So we have experiment 1, 2, and 3. We have a reaction of 2HI equilibrates. That's how we say that double-headed arrows equilibrates to H2 and I2. So I want you guys to calculate the K value from this graph, okay? I want Joy's group and Ricky's group to find the K value of this graph, and then Jaden's group over to find the K value of this graph. So you might want to write the reaction down. I'll put it back up there real fast. 2HI yields or equilibrates to H2 plus I2. Right, got that BCE down? 2HI yields or equilibrates to H2 plus I2. And then you're finding the equilibrium constant, also known as K value from these graphs. So if you can't read the number, let me know, okay? It's kind of small. Give me a thumbs up when you have your calculation. Shouldn't take you more than 30 more seconds. Alright, this group over here, from experiment 1, can you guys tell me what your K value was? Your equilibrium expression value? Okay. Middle-ish area? Well, somebody. 0.0288. I'm not checking these right now. I have my paper here in a second. Last area over here?
0.0184.
0.0184. Can the middle group tell me, can you guys just verify between each other? Tell me one more time. 183. You're good. Okay, yeah. If you don't write the equation or the expression out, most of us will forget there's a squared exponent there. That's why I always have you write your expression before you start plugging data in. So, what is it? Does the starting point of a reaction matter in terms of the equilibrium value? Not really. We're going to say no. Okay, so this is the same as this is the same as this. Well, they're all basically in the same ballpark. So the K value is not concentration dependent. What does K depend upon though? Temperature, right? So if you have endothermic reaction or exothermic reaction, raising temperature, lowering temperature would therefore change your K, which we'll get to shortly. Okay, so we saw the graph, we plugged in just the equilibrium values. But what you can know is, or what you can see now, is that I could technically ask you for changes over time. So like initially we had this, at equilibrium we had this, what was the change? So like if I see, according to this graph here, that's the red line for these two products. Here's my initial, here's my equilibrium. Could you find the change? Like if you could figure that value out right there. Definitely, right? If you had that value and you had your equilibrium value, you could determine the difference, and that's just subtraction. Same thing here. If this was your initial for HI, but the equilibrium was here, you could find the change. So if you find the change of one thing, you can find the change of the other thing because you have the stoichiometric relationship between them. So if this one changed by 4 moles, these are going to both change by less than 4, right? Because they're stoichiometrically 2-to-1 ratio. So what we're going to do is we're going to design our own change charts, which are called ICE, initial, change, equilibrium. That's different than BDA, because BDA we're assuming completion. We're assuming like a limiting reagent problem or just some amount of non-reversible reaction. So we call them differently. We call them ICE boxes in equilibrium. We're going to get there shortly. Okay. So one more slide of notes. Q. Do you guys read about Q in your reading? Yes. For download the information on Q charts. Actually, this computer takes forever and a day to get logged on. If you're not logged on yet, go and log on. You can start out and you can put your computer back in the log station for a minute. So you were writing notes on the board right now, but you're just logged on to the computer. So when we find a equilibrium constant, the only thing, we've only done this a couple times now, but the only thing we plug into the equilibrium constant are equilibrium values, or equilibrium concentrations, equilibrium partial pressures. So the equilibrium constant, we plug equilibrium values. But for the Q constant, or the reaction quotient as it's called, you don't plug in equilibrium values, you plug in initial values. So what you're doing is, once you plug in these initial values or concentrations, which is our normal one, you could plug in initial partial pressures as well. You're saying, okay, here's the initial setup, here's the initial condition. Obviously, I'm not at equilibrium yet, but which way do I need to go with the reaction? Do I need to make reactants go to products, or do I need to make products go to reactants to achieve equilibrium? So, the question that would prompt you to find Q is this question up here. Is this reaction at equilibrium? Has equilibrium been reached? Has equilibrium been achieved? So that's your prompt. That's your saying, okay, find Q. So you go find Q and compare to K. And so the comparisons are down here. If Q, when you plug in the data points, if Q is equal to K, you're like, yep, it's the same as the equilibrium constant. Equilibrium has been achieved. We are done. Dynamic equilibrium is just occurring as is. If the Q is large, let's just do a quick reminder what Q setup would be. Okay, so before so just halt and write for just a minute. I said it's found just like K. So how would I set up Q? Products over reactants, right? So it's still products over reactants in terms of their concentrations. But I'm going to put a little O, which usually means initial, right there. So Q is big. What here is making Q large? Products or reactants? Products, because the products are in the numerator, and if they're large, they raise the number. So if the products are large, there's a lot of them, that technically, and overall, that makes the Q value larger than K value. That means you got too many products. You got to get rid of them. So which direction do you flow to get rid of products? To the left, to make more reactants, right? So that's why we proceed from products to consume them towards reactants to create them. And so that's going to modify our Q to make the products go down, the reactants go up, to the point at which Q would equal K. And once we have Q equaling K, then the process kind of stops and equilibrium will ensue. So what does this look like in a problem? Let me just get a little space here. What this looks like is you might have a reaction, and I have like 1 molar of A and 1 molar of B. Okay, so if I plug this into Q if I plug this into Q compared to the K, and Q is large, what I would do is proceed towards the reactants by subtracting products and producing reactants. So it's like your BDA where you're subtracting from one side, adding to the other. It's just knowing which way to go about it. Same thing down here. How does Q become too small? So you have too many reactants, which is why on your products divided by reactants, the value is low, because if you have a large value down here, the number is driven down. So how do you get rid of too many reactants? You react them, right? So you consume that side. So you'd have A equilibrates to B, 1 molar, and you'd subtract from A while adding to B. So this is how we'll be setting this up. Yeah.
How do you find the value that you subtract
Well, it depends on the scenario given. It's usually you're going to solve for that yourself using algebra. Okay. So what we're going to do is we're going to do a quick exercise with Q equals K, or Q compared to K. It's not going to be equal. This is, This is on. I'm bouncing around some because I'm not ready to do ice boxes with you yet. This, I think, is on your paper. If not, just use it for what's up on the board. It could be there someplace. So consider this reaction. In which direction will the reaction proceed, left or right, if we start with these following conditions? So how would you approach this? Dad, help me out. Well, it's giving you these concentrations. It's saying that this is what we're starting with. Okay, so find Q with these. Okay, so how do I set up Q for this reaction?
You're gonna use your product, so it's gonna be NO.
Nitrogen monoxide. Okay. Okay. So this is our expression for K or Q. It's the same expression, but we're plugging in 0.1 molar for all of them. So 0.1 molar squared, 0.1 molar over 0.1 molar squared. No calculator, guys. What is this? 0.1. Good, because this 0.1 squared cancels. Okay, so this Q is 0.10. No units. Okay, Q and K are unitless. So this is Q, right, guys? What do I compare this to? The K that's given up here. So Q is less than K. Think about what that means in reference to the relationship of products to reactants. Don't memorize, oh, if Q is less, then it goes this way. If Q is greater, it goes this way. Don't try to memorize it. Think mathematically. So Q is what? Low. Okay, so how do I get Q higher? Make more what? Make more products and consume reactants, because we're going to make that numerator high, the denominator low. So if the Q is low, then we're going to proceed which way? Proceed right. Good. That's it. Now, we eventually will be setting up the ice boxes and plugging in and finding X values, but I just want to make sure you're clear on how to do that first. Okay? Do me a favor. I'm not going to do the second one for a moment. Go down to, I'll do these in a minute. Go to this website, teachchemistry.org/. Okay. I think you're good, but I gotta see where you are before I do. I can kill you with the example problem. Okay. I don't really want to have to until you tell me where we are. Teachchemistry.org /K. So there's like a little quiz. It's not really a quiz, it's just a quick practice. So I think there are 15 questions, but take a minute and try a couple of those to make sure you're confident in what you're doing. Of course, calculator active. Yeah. Mental math. Talk to your neighbor. I'm not sure if they're randomized or if they go in sync order. So you can work with a neighbor if you want to. Just take a couple minutes to practice. All right, find the question that looks like this under your, in your packet. If you have it, it's just a big table. Okay, so this is kind of the introduction to how we want to approach an ice box, but we're looking for changes from an initial concentration to an equilibrium concentration. So complete the chart for the reaction below and calculate the value of K for the equilibrium constant. We're given this reaction a 1 to 2 to 1 ratio. We're given an initial amount of A, B, and a none for C, and it's not because it's like, guess what C is? It's because it's at time 0, it's telling us that we don't have any C. So let's go ahead and put 0 there. The molarity is denoted at the top, so I'm good to go. I'm not going to put the units as well. So look at the change over the time. This is change. From 0 to 20 seconds, what happened to A? Decreased by what? 0.05. Okay, so we subtracted, so it's decreasing by 0.05 molar, and we made it to here, right? So tell me, how would that play into B and C? Subtract how much from B? Yeah, subtract how much from B? So I'm going to put a ratio of 2 times 0.05. Okay, so that's technically subtracting 0.1, which would leave us with what? So 0.150. And then how much C is, well, tell me what's happening to C. Okay, so there's a production here, so it's a 1 to 1 ratio. So we're adding 0.05, so we end up with 0.05 at the end. Okay, so just like a BDA, right? Except we're not completely consuming one, we're just doing it in baby steps. Okay, so keep going. Now from time 20 times 40, we know one piece of information. We know that C now is 0.075. So what changed with C? We added what? 0.0. Thank you. It's going to be louder, and I can do the math. So from here to here, it added 0.025. So then what happened to B? Right? These were two reactants. So we're producing products, we're consuming reactants, we're subtracting what? So 2 times 0.025, which is 0.05. So then what's this final answer here? 0.1. Okay, so this is basically like a equal sign right here, where those darkened lines are. Okay, so B was manipulated by the same variable. A is as well, but we're subtracting not 2, but 1 here. 1 times 0.025. So this is what? 0.125, okay? So what we're going to look for is equilibrium to be achieved. Has equilibrium been achieved yet? No, so it's 0.02, it's 0.015, it's 0.0125, so we haven't met a constant concentration yet. So keep going. So from 40 to 60, we have one given piece of given information. So what happened to B? Decreased by 0.03 molar. Okay. So what is C? What happens to C? It went up by 0.0. I think B and C are in the same ratio. Oh, thank you. I can't keep it all on board at the same time. Okay, so this is increased. Oops, this is increased. Let me write this a little differently. So we know that they're all increasing or being manipulated by a value of x, which is plot x. So this is twice as much as everything else. So this was 2x. So this was 2 times what value? 0.015. So that's what we just said. It was 0.03, but this gives you an indication of how C and A are going to change. So this is adding that value, and this is subtracting that same value. So this is what? A is what? 0.110. This is what it is, and this is 0.09. Thank you. So, has equilibrium been met yet? No, because I still have values changing. So then what you're going to see is eventually we can keep doing that. Eventually we'll meet equilibrium, and then we would have a condition that we could then plug into what? The K expression to solve for K. So once I keep doing this, I get down to equilibrium values. How do I know it's at equilibrium one more time? Concentrations are constant, so they're unchanging, which means we met the zero slope graph, which means we take those values and plug them into K. Alrighty? I just want to make sure you could deliver on looking how changes over time occurred. Alright, let's keep going. And this next part, tell me how you would do this. I think you can do this. Just tell me how you would do it. Raise your hand when you're ready. It's not hard. You got this. Raise your hand when you're ready. Cassie, what you got? Right, so you'd have to write the expression first, right? These are all the 1 to 1 to 1, they're all gaseous, so I'm going to plug them all in. Plug, plug, plug. The key word, though, that you have to see to just plug into the equilibrium constant is the word at equilibrium. So this one says it's at equilibrium, so that's why all of these values here, you can plug straight into K EQ, because remember, KEQ is an equilibrium constant. So if it doesn't say at equilibrium, we have to go through and do an icebox. So I just want to make sure you're looking for the words at equilibrium. Are we clear here? Okay. All right, so here's one where the conditions are not given strictly at equilibrium. So I'm going to teach you how to icebox, which is the initial change in equilibrium. You maybe have not picked this up yet, but when we were doing BDAs, what units do we always use in BDAs? Moles, right? So BDA uses moles. But if you're putting data into equilibrium constants, you're using concentrations, molarity, or partial pressure. So that's one thing just to be clear on when we're using moles versus not. All right, so a student placed 0.2 moles of phosphorus trichloride and 0.1 moles of chlorine gas into a 1 liter flask. The reaction shown below to allow to reach equilibrium, at which at that time it was found that the flask contained 0.12 moles of phosphorus trichloride. Do you notice how it's giving you initial concentrations and then in one final? Do you see that between the lines? So it says they placed this much into a flask. This means initial. And then blah, 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 we met equilibrium, or we achieved equilibrium. And then at that point, it contained this. So now, since we see both, we have to set up an ice box. So go ahead and write your reaction out. I know it's on your paper, but you probably don't have space, so write this out. And then next to it, just put ICE, like you would BDA. If you're really feeling kind of crazy, you can put a rice table, because that's the reaction. And then we're going to write the initial conditions and then final. So, all right, so what are the initial conditions for PCl3? 0.2 moles over 1 liter. I can do that in my head, right? What is this? 0.2 molar. Please put your units in there because it'll kind of trigger for you to think about, are my units correct? Okay, and then we're given 0.1 moles of Cl2 in 1 liter. So the same we can do the same thing, molarity here. So this is 0.10. And since it's omitting the fact that we don't put any phosphorus tetrachloride in there, what are you going to put here? 0 initially. Okay, so we have our initial conditions. We also know only one final condition, which is what? So that's what molarity? So 0.12 molar, since it's just moles per liter. So over the course of this reaction, how much did PCl3 change by? 0.08, okay? So I'm going to write this two ways. I'm going to write this as 0.08, which I'm going to call x. It's just an amount, but we actually know what the amount is because we had the final, so it was quite easy to figure that out. So we're going to subtract that amount of x from PCl3, but we're subtracting the same amount from chlorine because it's a 1-to-1 ratio. We're adding the same amount of x to PCl5 because it's a 1-to-1 ratio. This one's easy because it's 1-to-1-to-1 all the way through. So I'm subtracting x, which is the same as 0.08, and I'm adding x, which is the same as 0.08. So what do we have here for chlorine? 0.02 molar and 0.08 molar. Okay, so then now we have equilibrium, right? Since we have equilibrium, now the question was, well, there are a series of questions, but we just basically the whole thing at once. We're at equilibrium, so what could I then find? The K value, the equilibrium constant value. So guys, what's a Kc value? Look. You guys just let me know when you're ready. What is it? 33.33 all the way. Okay, so who's favorite, products or reactants? Products, and when you graph it, who's on top? Products, okay. So how are we feeling about ice? This was an easy one. You were given the final, so no guessing on what X was. It was easy. You just had to subtract to figure out what it was. All right, so we got the initial concentrations, changes, we got that. So I just walked you through the process all at once. And then I want you guys to find the value of Kp as well. Okay, so from that data, you guys may not have this question right in front of you, so you're solving for Kp, given this information above. 523. Over. If there were aqueous species, you probably would not be finding KP because KP is all about pressure, pressure, pressure. So it's not going to be all gaseous, really. So, answer: what do we get for KP? 0.77 something. Okay. So, as you can see, with respect to the way the KCs are relayed, it's showing with concentration respect. KC is showing products are being favored, but partial pressure is being included. It's showing the reactants being favored as relates to pressure. It's weird because of the -1 exponent. How do we get this -1, by the way? Right. Good. So 1 mole of gaseous products minus 2 moles of gaseous reactants. Question? Yeah. So you're just relating moles to moles of gas to moles of gas. Okay. Let's do this one. I kind of bold them, the words that are important. Okay, so ignore the top instructions. Let's just look at number 1 here. The equilibrium constant for the reaction below is blah, blah, blah. If the initial concentrations of A and B are 0.15 and 0.28, what is the equilibrium concentration of C? Okay, we're going to talk first on how to do that. And then, once you have a clear problem-solving process, try it. Let's see if you first. I'm hearing some incorrect things. Just making that known. Raise your hand if you have a clear problem-solving process. See what you think. Louder powder, please. Come on.
You just used it with the real expression behind the final concentrations.
How? Do we have all the other equilibrium concentrations to plug into that? No, we have initial concentrations. These are not equilibrium concentrations. We cannot just plug right into KC. All right, we will have to do that at the end, but how do I get started? JT? Okay, so let's set up an ice. Do I know the changes? Yay or nay? Okay, so if I don't know the changes, I'm going to call them what? X. Okay, and I can make an appropriate number of X's, like 2X's, 3X's, 5X's, whatever. Okay, so we're going to solve for X's using algebra. Ready? All right, so set up an ice. Or write your equation out first because you guys probably don't have this some space on your paper. So through 2A plus B equilibrates to 3C. Initial conditions, right? So very clear. Initial conditions of A and B are 0.15 and 0.28. So it's basically by omission, it's telling you that there is no C initially. Okay, so we know A and B have to react to form C. I have to subtract A and B to form C. So how much of A should I subtract? Minus 2x. So I don't know what the amount is, but I know I can solve for it. And I know there's a ratio, x to x to x, but it's 2x's to 1x's to 3x. So how much of B do I subtract? 1x. How much of C do I make? 3x. Okay, so then at equilibrium, I'm going to have some funky algebra. Okay, so this is 0.15 minus 2x. At equilibrium for B, it's just 0.28 minus x. and at C we have 3x made. So these are the values, I say values loosely, those are the values we plug into the KC expression. Okay, so I'm going to see if I can make myself some space real fast. All right, so Emily, what is the KC expression? Actually, will you tell me it with these variables first before you start plugging the data in? So just give me the expression, yeah. So the concentration of C raised to the third over. Good. Okay, so you must write your expression first because I guarantee you, you'll forget to do something with that 3 or the 2 or whatnot. Okay, so then now we're going to plug in for C at equilibrium. What is it? It's 3x, right? But that's 3x still raised to the third power. Okay, divided by, what's A at equilibrium? 0.15 minus 2x squared times what for B? 0.28 minus x to the first. Ooh, doggies, right? So this is equivalent to the k value given, 1.5 times 10 to the negative 8 units. All right, I want to solve for x because x, once I know x, I can multiply it by 3 and I can solve for the C's final concentration at equilibrium. How would you solve for x? Let's simplify everything, okay? You start for a minute. I still need more space, apparently. So there'll be some mathy, and then there'll be some that are simplified like that, and we're done, okay? So this is what? So 3 times 3 times 3 is 27 x cubed divided by, you'd have to square this and then FOIL, okay? So what I'm showing you first is that it can get complex, but I want you to see some points here. Okay, so we can FOIL out, we can square and then FOIL out, but overall, what's happening in this reaction? Look at the K value. Who's favored? Like super duper favored, right? So essentially, are you guys thinking that these reactants are reacting very much? Probably not, because they're so favored, they don't want to get rid of themselves. They want to maintain a high quantity of themselves. So do you think this X value that we're subtracting is large or small? Very, very small. Probably infinitesimally small. So do you think that X value that we're making is very small or very large? Also very small. So what we do is, when we see that the math is challenging, AP Chem does not go barely past the quadratic equation. Okay? So if you're getting past quadratic, you're doing it like you're making your life too hard. Okay? So obviously we're at that point, right? So we have to make a decision. Do I solve this? Heck no. So this right here is something called neglecting X. And it's only if, I'll say this with caution, it's only if the value of X seemingly is quite small. But we figure that out by looking at the K value and saying, well, that looks like the reactants are pretty darn favored. I don't think very many of them are going to react. Let's try to make the math easy, okay? So only if X seems like should be small. And I'll give you more rules of how you know that. But let me show you what it means to neglect X. I think that this 2X right here is so small I can ignore it. So you put a little arrow through it, put a 0. You do the same thing for this other X. But there's nothing here to add or subtract X to, so we must keep this X. We're only going to neglect X for plus or minus X. So you're not doing it for a standalone X because you're not, you do need to find a value for X, so we can't knock all the X's out or we'd have no X's to solve for it. So it's only for the ones that are being added or subtracted from a quite large number, apparently, compared to this. So I'm going to now take this out and this out. Now simplify. So the same applies on the numerator, right? So KC is equal to 27x cubed over what? All right, so what's 0.15 squared times 0.28? 0063? Thanks. 0.0063, so we just did this squared and times it by the 0.28. This equals 1.5 times 10 to the negative 8. Now, you guys solve for x. I wasn't going to teach you this one today, but you're doing great. We'll do some more neglecting x tomorrow. Right, so did we get to the point where we isolated x cubed? What was x cubed when you isolated? 3.5 times 10 to the negative 12, okay? So then we're cube rooting, or raising to the 1/3 power is the same thing. What is x? 1.52 times 10 to the negative 4th. And x represents what unit? Molarity, thank you. This x has a unit, right? K doesn't have a unit, but x has a unit because it's representing concentration changes. So this is x, okay? What is concentration of C at equilibrium? So how much times this? So 3 times x, so 3x is equal to concentration of C, which is whatever that is times 3. 4.55 times 10 to the negative 4th molar. All right, so now we did all this assuming that we thought correctly and thought x was so tiny we ignored it from the changes in concentration, but we utilized it for solving for C. How do we prove that at the end? And this is a necessary step. You have to take, I need some more space again. You have to take the x you solved for. Okay, so here's my process. So to show okay to neglect x, you have to take the x, and you're basically proving or trying to say that x is no more than 5%. You guys know the 5% rule from stats, like p-value less than 0.05. Who knows what I'm talking about? No, we are not going to that level. It's just a relationship to saying, like, this is statistically insignificant. So if x is statistically insignificant and doesn't make a big margin of error in our calculations, we are allowed to neglect it. But the only way you show that is by saying x divided by the largest number sorry, not largest, smallest. I just have to do a quick thought. Smallest number you would have added or subtracted it from, times 100. And if this is less than 5%, we are good. It is an insignificant amount of change that we just modified, meaning it's statistically insignificant. One second. So what this means, in accordance with what we calculated, was we would take this x, right? So 1.52 times 10 to the negative 4th, and we would divide x by the smallest number we would have added or subtracted it to, which is up here. Which of these is the smaller number I would have added or subtracted from? 0.15, right? So this right here. So basically, you have to see your work to really support where you're going. So it's 0.15 times 100. What percent is that? What is it? What's the percent? 0.1%. Okay. Is that smaller or greater than 5%? A lot smaller. So yes, this is smaller than 5%. So you are good to neglect x. If it were greater than 5%, you'd be doing some cube. You'd be probably plugging this in your solver and your calculator. Okay. Does anybody know how to use the solver or the calculator? Oh gosh, your math teacher's gonna kill me. So I'll show you how to do that shortly. If I don't show you today, I'll show you tomorrow. Last year, Miss Morara about killed me, but it's a necessary step. Okay. All right. So neglecting x. Talk to the person next to you about the entire process we just did, just to clarify that you understood. You picked up where we were going. You didn't understand it yet. You picked up where we're going. Are you in your solver? Nope. Don't do it yet. All right, so let's come back to me. Okay, we will practice neglecting X much more tomorrow, but the idea is that if we did find a way to simplify our math to the point where it was not going to impact our final answer, we should. Margaret said she calculated all the way through without neglecting. She just kind of rolled out the squared and foiling out and isolating X, and we got the same answer. Yes? Okay, so it was infinitesimally small, so we were able to say there was a statistical insignificance by neglecting X. Okay? Yeah.
So is it easy just to not neglect X in cases of
No. You ain't got that kind of time. Okay, you do not. We went through this very slow, but in the future you would not have time to run through all that. Okay?
Is it just cancel out though? Like, you have 27 X comes off, and you have 4 down below.
No, no. This would be subtracted. You cannot you cannot cancel something that's by itself with something that's being subtracted. They'd all be multiplied on the bottom to cancel. We'll review simple math. Yeah. I would include more sig figs, so hopefully I could not be that close. I don't know. It depends on how many sig figs you use, but if it was 5.1, I wouldn't say it would be neglectable. But hopefully we'll run into that ever, okay? Can we switch modes? Let's go back to easy stuff. Pull back out your problem or pull out your packet. Okay, we're going to do more of this tomorrow. So in your packet is a problem set called, it says, we're doing practice and neglecting X tomorrow. Okay, it says AP Chemistry calculating equilibrium concentrations 1 through 10. Okay, so let's take about 10 minutes right now. It's on the second page. It is upper right-hand side. Some keywords to look for is if it says at equilibrium, keyword. Here we go. Plug that in K. If it does not say at equilibrium, it gives you initial. So that's ice. Some of the now this was a very difficult, challenging math one. But if you had something like, this is what it looks like, by the way. If you had something that was like x squared over 0.1 squared, like you could simplify by square rooting both and make yourself a solution for x quite easy. So let's get started on one, and then so forth, and chat with me, chat with your partner, see what you need to do. Andrew, I'll just take your phone.
Oh, no.
You good?
It's not right on it.
Oh, okay, okay, you can. Feel free to put your laptop up if you feel like you need to. You got 10 minutes. I would think you log off for